Hey Kev,
Yeah, it's Jono.
it's almost footy season, and that means uni's going back soon, so maybe we should be like choosing subjects and stuff.
You gonna do that WAM booster on creative accounting?
Yeah, nah, thinking of pushing myself. Uh, I did that classical mechanics course last year, the one with a dude with the totes rad video set up. Well, he's given a course on quantum mechanics this term, and it sounds like it could be kind of fun.
Yeah, sounds a bit fringe.
Oh, don't know about that. I was watching on the telly the other day this quantum computing stuff. Apparently, it's like the next boom industry. Like Microsoft totes into it, and maybe once all this is done, I can get a job and I can make more money than the football players even, and then wouldn't have to live in this dump on welfare.
Must prosper, Jono, must prosper.
The best part of summer is over, and so whether it's football or university, it's time for a new season. Hopefully, this season's as fun as the last one, maybe even more fun. The topic this time is quantum mechanics, and it's a subject that's notoriously difficult to teach. Some of you will be familiar with some of the sort of little early concepts of it from your first year courses. You may be aware that there's of an uncertainty principle. You might know a little bit about atomic structure. You might have even seen what a wave function is and a Schrodinger and the idea of the Schrodinger equation. There's two ways to teach the subject, and the most common often way is to keep going down that line of Schrodinger equations. So you look at ideas like the infinite square potential well, and then various different potentials for how quantum mechanics works. And it's difficult because you get some way through the subject before you build a rigorous mathematical framework that handles all the problems, which means you kind of go some way and then start again. And also I find it leads you into some concepts that are rather misleading and very difficult to undo once you get used to thinking about them. So ideas like wave-particle duality, which I now really hate, you can avoid by not teaching it down that road. So the other route to doing it is to basically go to looking at how angular momentum behaves in quantum mechanics. And it's nice because it allows you to build a mathematical framework immediately that covers the entire subject. You spread that back out to get to the point where you handle the sorts of problems you see a little bit of in first year. And in some ways it kind of enables you to at least sidestep, because you have a rigorous mathematical framework, some of the weird and misleading concepts that come up in quantum mechanics. So that's probably the best place to kick off, so let's do it. I want to start this course with looking at a system that you're probably familiar with from classical physics. And when I mean classical physics, I pretty much mean everything you learn up until you do your first course on quantum mechanics. And that is spinning objects, right? One of the problems we have with quantum mechanics is that when you come through classical mechanics, it's easier to teach because you have something on the order of 10 to 20 years worth of experience of what the classical world is like. So you can come in, we can talk to you about accelerating a car, we can talk to you about jumping out of a plane, we can talk to you about firing projectiles, because you've seen and done these things. You kind of know intuitively a little bit how they behave. And then building a mathematical framework for that is easy because you kind of know what behaviors you're trying to describe. The challenge with quantum mechanics is that you've never lived in that world. You've never seen what the reality experimentally is for those types of systems. And in order to build a mathematical framework for it, you kind of have to have some feeling of what you're building the framework for. So the focus of this first lecture is basically for me to try and take well over 100 years of experiments on quantum mechanical systems, many of which we can't give you in labs and we can't do as demos and you can't really experience easily for yourself, and distill them down into a sort of a simple starting picture for how quantum mechanics works and how it's different, so that you can understand why we need a separate mathematical model for it and how that mathematical model should work. Okay? And so the important thing here is that this in some ways is the most difficult lecture, and it's the most difficult lecture in the sense that the ideas here will be new. They will not fit with your experience of the world, so they will seem weird. And you're going to have to accept them because they're experimental reality. We can do experiments, we can prove that it works like this, even though it works in a way that we think naively, because we've never experienced that world, is weird, okay? And it's difficult because it's easy to go, that was the first lecture, I'll forget about it and I'll get into the course. And what you really need to do is keep coming back to this lecture, not watching the video again and again and again, but you need to keep connecting everything that follows this back to the ideas that come in this first lecture. So you'll want to spend a fair bit of time in this first week getting your head around what's going on here. And some of it will be confusing and you'll have lots of questions, and that's good. You should ask those questions because that's part of unpicking the subject. And later on, you'll end up with things that don't fit together and ideas that are wrong, and that's cool. You should pick that up because that's part of building the subject as well. But you really need to keep confronting yourself with what you learn in this first lecture in the later parts of the mathematics in order for it to make sense in a way that you can kind of answer questions by understanding the system rather than just pulling nuggets of memory from your head, okay? All right, so to football. We have a spinning object in classical physics, right? And we know that if we have a spinning object, there's a plane of rotation where, you know, you've got objects going in a circle, and perpendicular to that plane, or the axis of rotation, will align with the angular momentum for that object. So if I have a football spinning like this, the angular momentum points this way. If it spins like this, the angular momentum points this way. Okay. The other thing we know from classical physics is that for any vector, angular momentum is just one of them. You can do it with force, you can do it with velocity. We can basically take that vector pointing in some arbitrary direction. We can set up an x, a y, a z axis, and we can make projections using trigonometry of that vector quantity onto those axes. So we can get an angular momentum projection in z, Lz, Ly, and Lx. We can do calculations with those in the independent directions, and then if we want, we can rebuild that back into the original vector, okay? And the other thing that we know is that it's actually relatively easy for us to tell, maybe not the magnitude, but at least the direction of the angular momentum at any point in time, because all we have to do is look at the system and look at which way it's rotating, and that will tell us which way the angular momentum points, okay? There's one other feature of rotating systems that you probably haven't seen in your courses yet. Some of you might. Usually it's taught in second year mechanics, but it's a fairly easy to understand idea that we'll go through now, which is precession. So if you have a spinning object, and most of you will be familiar with this from, you know, playing with spinning tops when you're a kid. If you have a spinning object, it will spin quite happily on its axis if it's perfectly balanced. And then what happens is it'll tip a little bit. When it tips a little bit, it's subject to a force, which is just gravity, that tries to pull it over, right? When you have a force acting on an object with an angular momentum, you'll generate a torque that's perpendicular to the plane set by the force, which is gravity, and the angular momentum, which is pointing this way. And so you'll get a torque that points that way. And so torques drive rotational motion, right? Force drives rotational motion. So it'll push it around like this, and now, of course, it's perpendicular, so this thing will go round and it will follow around like this, okay? So spinning systems don't always necessarily spin with the angular momentum constant. Often what happens is the magnitude of the angular momentum is constant, and the angular momentum vector will sort of do this pirouetting motion around some other axis that we define in space, and this is a thing called precession, okay? Happens in classical physics, happens in quantum mechanics as well. All right, now what we're going to do is we're going to take our classical object, which is just a football, right? So anytime when I talk about classic physics, I want you to think back to this football. Then we're also going to think about quantum mechanics. And what I'm going to do in quantum mechanics is assume that my spinning object is an electron for now, okay? And one thing you'll know from PHYS1b when you do electromagnetism is that if you have a current flowing, it will generate a magnetic field, right? So if you have a current flowing in a wire, you get a magnetic field that wraps around that wire, and you can detect that by basically running the wire through a piece of paper with some iron filings on it and look at the circles in the iron filings. You can take that idea of a current carrying wire and you can build it up into a solenoid, just like up in the top right here. And the nice thing about solenoids is that you can direct that magnetic field so that it runs along some direction, which is parallel to the axis of the solenoid. And you can take that idea of a solenoid back to the single turn limit and look at the current flowing through a ring. And there basically what you get is something that looks a little bit like a magnet. You get a thing called a magnetic dipole moment. And that magnetic dipole moment basically is the current flowing around that ring, generating a dipole moment that can then interact with another magnetic field. Okay? If you think about an electron has charge. Let's take a wrong picture for this. Long term it's a wrong picture. For now it's okay. Let's imagine that an electron is like this. It's got charge on it. When it's spinning on its own axis, you've got a little bit of charge here that's actually going around in a circle, and there's a whole pile of little charges in this thing that are going around in a circle. So it will generate its own magnetic field. Okay, so it has a dipole moment that can then interact with external magnetic fields. And just like you learn as a child when you play with magnets, if you have a magnet, it can point in any direction you like. You know, I can sit it on a table pointing this way or this way or this way. And if I then impose a magnetic field on it, what it would like to do is just align with that magnetic field. Okay, so there's an interaction between magnetic dipole moments and external magnetic fields that produces some alignment. And if I take that field away, that magnet will stay put where it is until I introduce a new magnetic field, in which case it will rotate to align with that magnetic field. Okay, that's the minimum energy configuration. I can also get a stable configuration where the magnet is anti-aligned with the magnetic field. And you have to align it quite well, because if it's a little bit off, it'll just flip over, right? But if you get it perfectly right, it's an unstable equilibrium where it will stay positioned there until you give it a nudge, right? So there's two possible ways you can align this magnet. It's with the field, which is stable, and it's against the field, which is unstable. If you give it a little nudge, it will flip over, okay? So that's how magnets behave. You're familiar with that idea. And of course, this picture of the electron as a solid object with charge in it ultimately is wrong. And if you do physics long enough, you'll learn how it's wrong and why it's wrong. But for this part of the course, that sort of slightly incorrect picture is good enough to give us the behaviors that are correct experimentally in terms of our understanding. Okay, so that's something that you'll later, if you do physics, you'll correct that idea of the electron as a sort of a ball of negative charge. Okay, so where we're going to start with this is one of the famous experiments of quantum mechanics. It's now 99 years old. It was done in 1922 by Otto Stern and Walter Gerlach. And the idea or concept behind it is rather simple. The implementation is difficult. I'll show you that in a minute. The idea is you have an oven. You heat up silver to a high enough temperature that it vaporizes and becomes a gas. And then that gas will basically move like gas. If you put it in a vacuum, the atoms can travel in straight lines over very, very long distances without colliding with anything. And if you put a slit in front, you can basically make a beam of atoms that are traveling through space, okay? And the velocity they have is just coming from their temperature. You can then direct them through a magnetic field set by a pair of magnets. And that magnetic field is set up in a somewhat special way so that instead of being all the lines aligned with each other, they sort of spread a little bit like this, okay? And you get them to spread a little bit basically just by shaping the ends of these poles, okay? It's not too important for where we're going, but this is how they do the trick. And then that beam of silver atoms arrives over here on a plate, where it just sticks, and that gives you your measurement, okay? As you know, in the 1920s, they didn't have digital cameras and stuff, so they have to use some fairly elementary methods for doing this. Okay, so if you take this apparatus and you pull the magnet out, what you would expect to get is a beam of atoms coming through a slit. They'll come up against the screen, and so you should just get a line on it, right? And sure enough, that's exactly what you get. What you would expect when you put the magnet in is that you've got all these little electrons. They're all spinning with different directions. And so they've all got little dipole moments. And depending which way their dipole moment is pointing, they'll either fly along and go up in the magnetic field, or they'll fly along and go down in the magnetic field. And that comes about simply because that magnetic field is sort of like this rather than a straight line, right? They're actually trying to move either as dipoles towards the tighter field or as dipoles away from the tighter field, okay? Hopefully you've seen that for electric dipoles in your first year physics course. Because you've got a whole spread of these things, you would kind of expect some go up more, some go down more, and you should just get this line that blurs out, okay? Now, the interesting thing about experiments is a lot of people come into them and think, oh, I'm going here, I'll get the right answer, everyone will think I'm a genius. Those are actually the boring experiments. The really important experiments that happen in physics are the ones where you come in with some preconceived notion and you get something else entirely. Those are important because they're actually interesting and they lead you to new understandings of things, okay? Often in physics, making mistakes is the best way to learn, and getting unexpected results is also the best way to learn. Your predictions are wrong. Awesome, this is going to be so much fun. So in the 1920s, they do this experiment, and sure enough, their prediction's wrong. They do the experiment, and instead of getting one line that blurs, they get one line that goes to two separate sharp lines. Some electrons have gone up, some electrons have gone down, but they've either all gone up to the same extent or they've all gone down to the same extent. What this tells them ultimately is that the dipole moment for all of the spins coming in here can only point in one of two directions. They're either pointing up, in which case they go up, or they're pointing down, in which case they go down, okay? And they're not somewhere in between, okay? So we're already seeing one of the features of quantum mechanics, which is you're kind of familiar with from thinking about magnetic fields. The angular momentum just won't point any direction randomly that it likes when it's in a magnetic field. It'll either align with a field or it won't align with a field. Okay, nothing really unusual here in some senses. What's also interesting here is that if you measure the total angular momentum of this electron and you measure what the angular momentum component in the z direction is, you try to think about it like a classical particle. Those two things are not equal. So what we basically find out is that if an electron is spinning, it's actually precessing around that field in this direction, or it's precessing around the field in this direction. Okay, you'll learn more about that when you do later quantum mechanics courses. One of the things I'm really going to try and do in this lecture is actually push all the complexity aside, because I want a simplest possible system to work with, and then we can add all this complexity back into the problem later on. Okay, but I just want you to be aware of this, because some of you will go hunting online and looking for spin of electrons. You'll find this, it'll look different to what I'm about to teach you as quantum mechanics. You'll go, oh no, this guy's gone somewhere weird. It's more detailed than where we're going, but you'll come back to the detail later on, okay? So just quickly, often in physics we draw these nice schematic diagrams that make you think, oh, you know, I can go down to the second year teaching lab and do a Stern-Gerlach experiment. The reality is that often they're a hell of a lot more complicated, and so a few years ago I actually decided I wanted to try and buy a Stern-Gerlach experiment for the undergraduate teaching lab so that you could do this in your classes. And I put in for a quote, and basically it's 81,000 euros, which is a lot of money for an experiment like this, and it takes a long time to do the experiment. Okay, you can see here it's quite complicated. There's a vacuum system. Underneath the table there's a whole pile of pumps so that you can get this to really good vacuum, and then you have a whole pile of control systems for making this whole experiment work. Okay, so you'll see these nice pictures like this of Stern-Gerlach experiment. The reality is more like this, and this sort of holds for lots of quantum mechanic experiments. The easy ones are the exception rather than the rule, and in a lot of cases, if you want to do quantum mechanics experiments, you're looking at A, a lot of money, and B, a lot of time, because they're hard, okay? And so my challenge today is to get you familiar with some of the ideas of quantum mechanics in a way that is manageable within an hour and with a sensible budget, okay? All right, so there's a few key things I want to point in this lecture about the way angular momentum works for quantum systems, okay? And the first one is that outcomes are generally discrete in quantum mechanics. So you're familiar with this from just thinking about spin a little bit like magnets. There's only two allowed sort of orientations for spin of electron in a magnetic field. That is with spin up aligned along the magnetic field and spin down anti-aligned with the magnetic field, okay? You'll also know from probably doing a little bit of atomic structure that electrons spinning on its own axis is not the only thing that happens, and often it's actually going in a circle around a nucleus, or it's, you know, orbiting in some way around a nucleus. And so there's another angular momentum in here which we call the orbital angular momentum, that comes about because you've now got a charge going around a circle, which generates a magnetic moment that's different to the one spinning on its own axis, because its plane of rotation can be different to the plane of its spinning. And that one, for example, rather than having two different orientations, just up and just down, can have 3 or 5 or 7 depending on the situation. Okay, but the notable thing here is that not every possible outcome is available. And that is kind of a hallmark of quantum mechanics. Often, rather than seeing continuous change in a variable, in the sense, if you think of the classical football, the angular momentum can point in any direction I like, an infinite number of directions with an infinite number of magnitudes. In quantum mechanics, often there's a small, finite number of possibilities, all of which are equally spaced in some way. So for an electron, there's just up and down. And for electron orbiting a nucleus, there might be, very high up, flat, slightly down, very high down. Okay? Discrete versus continuum, quantum versus classical measurement. Okay? We'll come back to that as we go further along. Okay, so what I want to do to get started in this course is do a thing now that I call an abstraction. And to give you an analogy for this, I'm going to start with energy drinks. Most people may not be a Red Bull person in the morning, but most people are caffeine people in the morning. Kick off your day with a coffee or a tea or if you're me, a Red Bull, to kind of get yourself awake and going for the day, right? And if you really think about that drink, whether it's coffee or Red Bull or tea, you don't care about the can, you don't care about the label on the can, you don't care about the taste, you don't care about anything. What you care about is that buzz from the caffeine. And it's the common thing between coffee and tea and Red Bull. The three things are different, the three things come in different packages, the three things taste different, but the central common idea between them is the idea that you want caffeine, right? And so if you start to think about trying to come up with a theory for how this works, you realize you don't care what the drink is, you just care about the caffeine. I put caffeine into Adam doesn't fall asleep at 10 o'clock in the morning, right? We're going to do a very similar thing for our spin. We started out considering it to be an electron, and the only thing we really care about is its angular momentum. We don't care about the fact that it has a charge, and we don't care about the mass, and we don't care about a few other things as well, okay? And so what we can do is just push those things to the side, not worry about them for now, and just deal with angular momentum, okay? If you're familiar with computer science, you've probably seen these sorts of abstractions before where you sort of just, boil things down to the simplest possible concept. If you stick around in physics, you'll see this time and again, this idea of just stripping off the stuff that's not important. So we're going to do that for our electron now, and we're going to replace our electron with a thing that we're just going to call a quantum spin. It's the simplest and in some ways actually the most quantum system we can possibly deal with. And it's really just a single degree of freedom for angular momentum. And in order to distinguish it from spin, which we often call S, we're going to call it sigma, which is the Greek letter for S, okay? And we're going to allow it to take only two values. One value is +1 and the other value is -1, okay? And so you can kind of imagine, if we go back to our electron, there's a spin projection along the z-axis for an electron that's a half h-bar in one direction and minus a half h-bar in the other direction. If we kept that, I'd have you writing h-bar over 2 through the entire course and I'd drive you crazy. We'd start accumulating h-bar squareds and get confused. One of the nice things to do in physics often is just to make all the constants and all the annoying baggage go away. Later on in your theory courses, you'll take this to the extreme. You'll do things like set h-bar and c and the mass of the electron all to 1. At first, it's a really strange thing to get used to because all of a sudden you've no longer got any constants. But it actually makes things nice because you kind of push the baggage away and you can really get at the important quantities in what you're dealing with. We're going to do the same thing here. So what I'm going to do is basically set h-bar equal to 2 so that a half h-bar becomes 1 and my spin is only +1 and -1, okay? If it's helpful, you can just completely abstract the electron away even. And so you can treat this quantum spin much like a quantum coin where your +1 is kind of a heads, your -1 is kind of a tails, and all you're really doing is just flipping a coin in the air and it's either heads up or tails up, okay? That's one helpful way to think about it. Alternatively, some of you have probably read about quantum computing a little bit because it's a bit of a sexy topic at the moment. And I'll give a lecture right at the end of my part of the course that's not examinable, it's just a fun lecture on quantum computing. So we'll come back to this idea later on. But you can also think about quantum bits as a similar sort of system. A +1 is a 1, a -1 is a 0, and so you can carry information in this idea of a quantum spin being up or down, which is basically the fundamental aspect of quantum computation. Okay, so there's our abstraction, of least of the thing that we're measuring and thinking about in this part of the course. Let's abstract our measurement as well. What we're going to do is basically take Stern-Gerlach experiment and stuff it in a box so that we don't have to worry about all the parts and all of the things that are going on, okay? And so we can kind of make a thing, let's call it a Qtron. It's a nice little measurement in a box, and basically what we do is we put a quantum spin into that box, beep bop boop on the inside. It will have some output that tells us what the angular momentum vector orientation for that quantum spin is, and then spit the quantum spin out the other side, okay? In some ways you can imagine this to be like classical measurement. I've got a spinning object, I then look at it, which is doing a measurement, and then it continues on its way out the other side, okay? So really we're just abstracting measurement to input, measure, output. Might have some controls that enable us to change the way the system does its measurement, but really we just have a box, and the box just does the measurements for us, okay? So let's take this black box and simplify it right down to just a function and what's important about that function. So the function is that it basically works at the single quantum spin level and tells you what the projection of the spin is along some preferred axis, right? And the way we set that preferred axis is basically to set the orientation of the north and south poles in a Stern-Gerlach experiment. We basically put our quantum spin in one end, have our magnets, it goes through, it either goes up, in which case it's a spin up, or it goes down, in which case it's a spin down. And then there's a processor on the inside that basically looks at which way it went, gives us the information out, either +1, it points up, -1, it points down. And the spin then comes out the other side of the machine so we can keep playing with it, right? We don't want to lose that thing. We might want to do more measurements down the line. And this is where the big difference between classical physics and quantum physics comes. It's the way that measurements interact with systems, which is why we want to be able to input, measure, output, okay? And then, of course, on this thing, we have an input, we have an output, we have an axis, which is basically which way our magnet's oriented, and then we have an output which will give us a -1 or a +1, or a question mark. And the question mark can be the case where it hasn't measured yet, or the question mark can be, I kind of don't know the answer yet, okay? Or something weird has happened, like an error light, okay? So I want you to take this idea of a little black box and think about the idea, as we go further forward, and think about just stacking them one after another, okay? If you're a guitar player, you're really familiar with this idea, using the same idea of same construct of guitar pedals. You'll hook, one after another, so that you can produce different things. You might come in, you put some distortion on. You might come in and put it, boost the volume, come out, knock out the lows, whatever you like. Sequence of these experiments. You can do the same thing with Stern-Gerlach experiments. You can basically have your beam come in through a magnetic field, take the ones that go up, not the ones that go down, take the ones that go up and feed them into another one, take what comes out the end, and so forth, on and on and on. And you can do this with a sequence that all have the arrows the same way, or you can do it with a sequence that have arrows pointing in different directions. So you can do big cascades of measurements, okay? And so one of the big chains of experiments in quantum mechanics has been doing exactly this, building ways of detecting what the spin orientation is, and then doing chains of them to understand how those measurements go together. All right? So before I start talking about what sort of experimental results we see, I want to get at the fundamental differences between classical physics and quantum physics, okay? So in classical physics, there's two important concepts. One is that a good measurement obtains the state of a system without altering it. What we mean by this is that the measurement is non-invasive. And so if I think back to my football, I can see it flying through the air. I can look at it, see which way it's rotating, know what the orientation of the angular momentum is, and it will just keep on its merry way with that angular momentum. Okay? And so me measuring the state of that system does not change the state of the system. It's a non-invasive measurement. Because that measurement's non-invasive, I can be sloppy and I can use the label describing the state of the system, in other words, what orientation the angular momentum has, interchangeably for my measurement of it, which is, what I know the angular momentum to be, because when I measure that, I know what it is and I haven't changed it, right? So in classical physics, you're probably used to the idea of temperature T being both a property of the system and a measurement, and those things are always the same, so you never distinguish between the two, okay? So this is where quantum mechanics, one of the big difficulties of quantum mechanics in terms of understanding how it works, is that both of those things get broken in quantum mechanical systems. So the first is that even the best measurements for quantum mechanical systems will always alter the state of the system. So if I think, for example, of having an electron that's spinning, moving through, let's imagine I can do something that I can't really do, which is look and watch how it's spinning. It's too small, it's impossible to do, but imagine I do it. What will happen is that look will actually disturb the system in such a way that it now changes its angular momentum, right? And so that measurement's invasive. It's doing what it does until I measure it. When I measure it, I change the state of that system. Because I can't see, what I have to do to interact with that system is essentially, with a Stern-Gerlach experiment, is put it in a magnetic field. And so before it comes into that magnetic field, the spin can be pointing any direction it wants. When it comes into that magnetic field, it's got to align. And then I measure it and go, well, it's either aligned with the field or against the field. And then after that measurement, it keeps going. But now the state of the system when it came in is different from the state of the system when it goes out, okay? And so there, what I've got to do is decouple my thinking about what states of systems are, like what the actual angular momentum is, and my measurement of it. Because when it comes in, I make a measurement of it, and that's a measurement of it at the point where I make that measurement. But I know that the measurement's invasive, and after that, I actually only know what the state of the system was at the point I measured it. After it, I don't know what it became because I'd have to do another measurement, okay? So in quantum mechanics, we've got to be really careful to separate states of systems from measurements because measurements are invasive, right? Really key idea. Okay, so what we can do now is we can take our Qtron and very quickly work through a sequence of measurements, just like you would do in an undergraduate lab. So you walk in, you've got a meter on the bench, you've read the instructions, because we just did that a few seconds ago, I told you how this works. And usually what you do, the first thing you do is you give it an easy measurement that you know what the outcome should be, right? So let me put a random spin in that I happen to kind of know what it is coming in, right? It's not quite up, it's a little bit off up, but it's sort of pointing along the up direction. And we'll talk later how you can make a state like that by measuring, but for now let's just assume that it's in that way, because it's out in space, not in a magnetic field. Comes into my Q meter or Qtron. I've got a magnetic field pointing up because that's my axis, and so I ask which way is the spin pointing, and of course it's sort of pointing along this up direction, right? So what I would expect to get is an up, and I do, right? I get an up on the end. But the interesting thing here and you can do more experiments to test this idea, what you find is that the state of the spin after the measurement is subtly different from the state of the spin before the measurement. Where when it comes in, it might be almost up, and then at the end of the measurement, it's up, right? We get the state of the system as what it is that we've measured in this particular case, okay? We'll get a +1, as you can see down here, so it works properly. Okay, so one of the nice things in experimental physics, and you should all be doing it when you're doing lab experiments, is not to trust one result, right? You expect repeatability. So what we should be able to do is now take this spin that we've put through this Stern-Gerlach experiment pointing up, put it back in the front and see what comes through. Okay, so let's do that. We could do this n times, and every single time we do it, our up, which is a perfect up, will measure as up and come out up on the other side, right? So this thing is completely repeatable. Experiment's not crazy, but let's go back to the experiment that we did in the first instance, where the spin is not exactly up, but it's coming in some initial state that's almost up. Not all of the time will we get it coming through this instrument pointing up. There's a small probability that we actually get it pointing down, right? And so this brings us to this to another aspect of quantum mechanics that's different from classical mechanics, which is that measurement is probabilistic. You don't tend to get results that, unless you set up the system in the right way, you don't tend to get results that are the same all the time. You often get results that have some probability aspect to them, right? And this is the first example of it. So some spin not quite up, looking it up, most of the time you'll get it coming through pointing up, and then every so often you'll get it coming through pointing down, okay? It's a rare result in this particular case. Now that we've got this thing pointing down, we can take that down and stick it back into the meter again. So we can do the repeatability test we just did. And if we do that, what we'll get is the spin down comes into our meter asking if it's up. Of course, it's pointing down, so we'll get a -1. And of course, it'll come out the end down, right? Because it'll come out in one of the two states that we have in this measurement. So this makes sense as well. We put it down into the meter, we measure it down, and it stays a down, and we always go through, okay? All right, everything's hunky-dory at this point. We can quickly do a test because we've always been measuring up, right? So what we can do is go, well, let's take the spin that we had pointing down, and now we'll set the axis so we're pointing down. We'll rotate the magnetic field by 180 degrees. Put down into the system, it will come out the other side as a down, and this time we'll get a +1 because now what we call +1 is basically the spin aligned with the magnetic field, and we change the direction of it, okay? So all we've really done here is prove that our ability to rotate the magnets does not change the outcomes of measurements in this system, okay? All right, so we've tested this thing, gives us a measurement. We've tested that there's some element of repeatability to it, but we sometimes get measurements that are unexpected, and we've tested if we change the field orientation that we get sensible outcomes from the field orientation. What we're going to do is our first really new experiment in here, right? And so what we're going to do is come in with a classical physics hypothesis and find an unexpected result. Imagine that we have a spin pointing down, and what we ask is, what is the component of the angular momentum along the x-axis? If we think about a classical spin, it's pointing purely down, so the component along this axis, this x-axis would be 0, right? If you think back to just vectors. In quantum mechanics, what happens is if we take a spin pointing down and we ask whether it's pointing to the right, what we will get is that it's pointing to the right. And as a single shot outcome, that's a rather weird thing to get, right? It's back with this where we had it almost pointing up and suddenly it comes out down. There's something strange about quantum mechanics in here, okay? Just to make sure that the meter hasn't just broken, we can take our pointing to the right and chuck it into a spin pointing to the right and chuck it into a meter that's pointing to the right. And of course it says, yeah, it's pointing to the right. And every time I put it in there, it's pointing to the right. Okay, so the meter's not broken. If I put in a spin pointing to the right, it will tell me it's pointing to the right. If I put one in pointing down, it tells me it's pointing to the right, which is really weird. Okay, so let's try this initial experiment here again, right? And let's do it a couple of times, because this is the same thing you do in experimental labs. If you get a weird result, do it again, do it again, do it again, do it again, and you'll soon find out whether the first measurement was just something weird and you did it wrong or whatever, or whether there's a pattern to this, okay? So first one, spin down, put it in, says it's pointing to the right. We do it again, put a spin down in, with measuring to the right. This time we get it pointing to the left, okay? This is a bit strange. We got two different outcomes, both of them unexpected. That just encourages us experimentally to do it more, right? So we do it again. This time we get it pointing to the right. Okay, fine. This time we do it again, we get it pointing to the right. Okay, so we've done the experiment 4 times. We get 2 different outcomes, both of which are unexpected. So what do? We just keep doing the experiment till we see what's going on, right? So let's do this. There's the first 4. There's the 5th, we get a -1. Do it 6th time, we get plus, minus. Let's just keep doing it again and again and again. Only outcomes we get are +1 and -1, right? We always get spin pointing right or spin pointing left. Keep working our way through. Same as you do in lab, build up some statistics, try and get a picture for what's going on. And now we're at the point where we're starting to see a pattern form. We either get +1 or we get -1. And sometimes we get strings of +1, sometimes we get strings of -1. What's going on here is we're getting a random result, okay? I just want to highlight something at this point, which a lot of students who come in to physics are actually not aware of, but this is a good point to point it out. The data I got up there is actually from a real trial of this experiment, and a lot of people think that random means +1, -1, +1, -1, +1, -1, +1, -1. Randomness is not smooth. And one way to demonstrate this is if you take a whole pile of hundreds and thousands, put them in a jar, shake the jar like mad, right? Randomize the hell out of it. And then have a really close look. What you'll notice is that there's this nice little cluster of green hundreds and thousands just here, and there's a little cluster of blue ones up here, right? And then there's whole spaces in here where there's actually not very many greens. Randomness actually tends to cluster in reality, and so this is actually once you're aware of this is a really cunning way to detect people trying to make fake random numbers, because if the distribution's too uniform, you know that it can't actually be really random. Someone's actually engineering this thing to try and make it what they think is random and isn't, okay? So this clustering we see in these results here, totally consistent with being random. If we now go through and look at the statistics and count, the number of times we get a +1 is 14 in 29. The number of times we get a -1 is 15 in 29. They're both heading towards 50%. And so what we're finding is that basically if we put a spin down in, we've got a 50-50 chance of getting a right or a left, okay? Now the interesting thing here is if you take all of the +1s and all of the -1s, and you add them all together, the sum of all those numbers is very close to 0. And if you do it for long enough, the sum of them is 0. And that's the result you would expect from the classical measurement, right? If you put a spin along Z and ask what the projection along the x-axis is, you would say it's 0. And what you're seeing here in this quantum mechanical measurement, if you repeat the measurement enough times, is that you get the outcome you would expect from the classical physics of the system, okay? Later on in the course, we'll see this as something we call the correspondence principle, and the value that you get in this large number of repeated trials is a thing that we call the expectation value, which is basically just the weighted average outcome of the results, right? But the one thing that should be really obvious to you here is that a lot of times in quantum mechanics, when you're doing measurements, the measurements are probabilistic. You will get outcomes, but not in a reliable way. You will get outcomes that are backed by probabilities, okay? So as we go in the next few lectures in the course, we're going to be expecting to build a mathematical framework that A, accounts for discrete outcomes, B, accounts for the fact that measurements are invasive, and C, accounts for the fact that measurements tend to be probabilistic, right? They're the three features that are very different to what we have in classical physics. Okay, I want to take this measurement to two last places before we finish for this half of the lecture. The first is I just want to reinforce the idea of invasiveness in measurements by setting up an experiment and looking at it from a classical perspective and a quantum perspective. So let's do the classical perspective first. Let's imagine we've got a football, right? Spinning on its axis like this, angular momentum pointing upwards. And what we do is we ask the question, is the angular momentum pointing up? It's equivalent to this first measurement here. And the answer is yes. And 100% of the time we will get that, right? We'll look, we'll go, yeah, it's pointing up, yeah, it's pointing up, yeah, it's pointing up, yeah, it's pointing up. Because the measurement's not invasive. Then what we would do in this second part here is go, is the spin pointing along the x-axis? And we would go, well, no, it's not. It's pointing upwards. I can see it, right? So we've got 100% outcome at the end of that, of the spin pointing upwards. And we basically go, I looked whether it was running along X, it wasn't running along X, right? And so here we would require our Qtron to give us an output that it shouldn't be able to give us, which is basically 0. It says it's not pointing along that axis, okay? Then I think classically, well, now I've got an up, and I ask the question, is it up? Yeah, it's up. I look at it, it's up. Is it down? No, it's not down, right? So if I consider the measurement up as the next in the sequence, I will definitely get an up. If I consider the measurement, is it pointing down as the next, I will get, no, it's pointing up, okay? And so, again, classical, all the way through the system, measurement doesn't change the state of the system. We just go from measurement to measurement to measurement to measurement, and you'll get the same thing, okay? This is like turning up in first year lab, measuring the length of a bench. Every time you measure the length of the bench, you get 1 meter, okay? And you should, it makes perfect sense. quantum mechanics has a feature that we tend to call demolition with measurement or invasive measurement. And the idea is that measurement changes the state of the system. So if we now think about doing the same cascade of decision making with a quantum system, imagine we start with spin pointing up. We ask if it's pointing up. Of course, it's pointing up, so we'll get 100% probability that we end up with spin pointing up at the other end, right? Something we built on in the first part of the test. Then what we would do is have our spin pointing up and ask if it points to the right. And of course, what we know is that the measurement of that is going to change the state of the system so that it either points along the magnetic field or against the magnetic field that we use to make the measurement. So the outcome will be that it points to the right or it points to the left. And there's a 50% outcome of each of those two things, right? And then you could imagine that we have this spin now pointing to the right and we ask, is it up? Now when we ask if it's up, what we will find is that it will either point up or it will point down. It won't keep pointing to the right, right? And so if you think your way through this, there's one possible outcome for this first measurement, which is that the spin was up and it's up. There's two possible outcomes for this second measurement, which is the spin points to the right or it points to the left. And then when we do this last measurement, there's four possible outcomes. If we ask if it's up, it could be up or it could be down. If we ask if it's down, it could be down or it's up, right? And so you'll notice that we got probabilistic outcomes coming all the way through this system. For example, if we ask pointing to right, pointing to up, there's four possible outcomes for that measurement. There's right up, right down, left up, and left down, right? And each of those have a probability of 25% of being the outcome, right? And so if we wanted to go back and test this, we'd have to do measurement after measurement after measurement to do it, and I'd bore you to death, okay? Just to give you an analogy to this, imagine going back into the first year lab, and what you do is you measure the length of the table, and it's 1 meter. And then I ask you to measure the length, the width of the table. So you take your ruler around the other side, you measure the width of the table, and you find that it's 50 centimeters. Now when you come back to measure the length of the table, you actually find that it's 7 meters long, right? This is one of the strange aspects of invasive measurement, where measurement changes the state of the system. So when you measure the first length, and then you do something else, and then you try to come back and repeat that initial measurement, you get a different answer. And so this is why in quantum mechanics you need to be really careful about how you do measurements, because that act of measurement changes the state of the system. Okay, there's one last experiment I want to do real quickly, which is just not to go into detail in, but just to consider. So imagine we take our Q meter and we do something really advanced with it now. What we do is we put in a spin pointing in some random direction. And then we put our axis for measurement to some random direction, right? It's not up, down, it's not left, right, it's just at some angle. What would be the outcome of this measurement? I'm going to tell you the answer to it without explaining why it's the answer to it, because around about lecture 6 or 7, we'll use our mathematical model to explain why this is the case as a way of validating our model, okay? But imagine I do this measurement. What I would do is put in this spin and measure it along this axis. And what I'll find is that some of the time I will get the spin pointing along that direction, and some of the time I will get the spin pointing opposite to that direction. The probability of getting it pointing along this +1 is the cos squared of half the angle between the direction coming in and the direction that I'm measuring, right? I'm not going to explain to you why that is. Later on we'll calculate that that's the case, and you'll have to trust me on this. If you do the experiment, you do get this result. And likewise, the probability of getting a -1 is 1 minus that probability, because probabilities have to add to 1. Okay, so here's sort of a final Qtron experiment that sets us up for later. We're going to set out in the next few lectures to build a mathematical model that enables us to predict the outcomes of these kinds of experiments. Okay. All right, we can't go on like for this forever. So let me just quickly summarize the 3 key things you should take away about how measurements are different in quantum mechanics. The first is that they're invasive. The act of measuring changes the state of the system. Second is that they're probabilistic. Often you'll get results that don't match on repeated measurements. And what you actually have to do is take a sequence of measurements to get what the probabilistic behavior of the system is. And the third one is often the outcomes of measurements are discrete rather than continuous. You get repeated examples of specific cases rather than any possible case in between. Invasive, probabilistic, quantized. All right. I'm going to stop on this first half and give you a break. It's pretty much everything we need to know about measurement. The second half, I want to be a little bit shorter. I want to cover one thing, which is how quantum mechanics and the act of measurement changes the way we have to think about logic. And there's two reasons for this. One, I want you to understand why what we call commutativity is important in quantum mechanics from an intuitive perspective. And I'm going to want that also later on as a way to justify why quantum computing is very, very different from the way we do classical computing. Okay, so let's take a break here, and I'll see you in the second half.